Yeah, so today I'm going to talk about identifying optimization opportunities and how to turn measurement data into savings. So why this topic? Well, gathering data is part of the task, but looking for issues is the other half of the task, which can be quite complex. And in this presentation, I will show you some examples on how you can combine signals and how that can lead to interesting insights on how to save and how to optimize. And I will give you some examples on that. Today or yesterday, actually, I was in a cookie factory. It's a pretty interesting story. We installed there a monitoring system and with some flow meters and kW meters, and it was nice to see how the people there on the maintenance department were looking at the flow data and were discussing like, hey, this department is baking cookies right now, and it's actually consuming 20% of all the compressed air, and the other department is doing nothing, and it's also consuming like 5%. So it can lead to interesting discussions on where to optimize, where to start saving. So common challenges with this. It's which signals should you measure? Well, Tim talked about that already. So you have to measure at least kW and flow, and also pressure. Temperature can also be very interesting, and in some cases, I would really recommend also to measure dew point. But it's also very important to understand the measurement uncertainties and their causes. Sometimes results can be overestimated if you're not aware of measurement uncertainties. What also is a challenge is sometimes to relate the results to real issues, because if in some cases you have an audit, but you don't know exactly where what the PNID is, how the system really looks like. I had cases sometimes you're looking at data, and after scrutinizing the PNID, then you'll find out, hey, there was a missing piece of equipment there that is causing this issue. So where to install sensors? Well, if you want to measure compressor performance, typically you would install a kW meter or an amp meter. That is less good, but it already gives you quite a good indication. You want to have a flow meter at the discharge pipe of the compressor. You need a pressure sensor. You need a temperature sensor. And you also might want to monitor the ambient conditions. And well, today I was actually at the gym, and I was on this this air-driven rowing machine, and I figured out they just cleaned that machine because it was I had to use much more muscle power at the same position as last time. And well, it's just like with turbo compressors. If the inlet is a little bit polluted, then there's less air coming in, and you will see that the amps of the motor will the current consumption will drop a little bit. So I had this very nice experience today while being on a rowing machine. Anyway, so at the demand side, you can also install flow meters, especially directly after the receiver tank, but you can also use flow meters to allocate costs to different departments, like in that cookie factory I visited. And it's all depending on what goal you have. As I mentioned, it's important to understand measurement uncertainties. And this is quite a complex subject for a 10-minute presentation. So I'm going to make it brief here. But it's important to know that if you're measuring, then every sensor you're using and also the equipment you're measuring has a certain uncertainty. And for example, an amp meter could have 1% full scale. A flow meter, when installed, can deviate maybe a couple of percent, up to 5%, because you don't know exactly the inner pipe diameter. You don't know the flow profile. There might be temperature swings that can affect the flow meter. The same for pressure sensors. A pressure sensor, typical industrial quality, is 0.5% full scale. Temperature sensor could be 1 degree off or maybe 2 degrees. And then there's the weather that can influence the equipment. And also what Tim already mentioned, there can be other things that change actually the behavior of equipment. And it's very important to be aware of this when discussing or evaluating results. And I think you should never debate anything when you're in the 1% range, because you first need to know the total measurement uncertainty. But especially with compressed air systems, it's not really possible to be within 1% accurate. That's virtually maybe only possible if you bring a compressor to a test lab. And system conditions can also change. So if you're measuring a short time, then you could have a bigger uncertainty on your measurement compared to measuring for a long time. And you have to take into account this seasonal weather and maybe also altitude influences on the equipment. So if you see a statement in a report or on a SCADA system screen with like 3 digits behind the decimal point, I would really doubt that figure. So it should be phrased properly, like it should be 30 CFM, as in this example, plus or minus 5%. Or a good statement could be it's between 28.5 and 31.5. So it should be within reason. So let's take a look at some examples. This is a typical P&ID of a compressed air system where one compressor, there's a dryer, and there are some filters. And in this case, the customer was interested in the pressure loss over a piece of pipe and or part of the network. And with this, you can reveal interesting things like maybe there is an issue with the receiver, maybe the line size is too small, maybe the filters are clogged, maybe something is not properly tuned. And so you can use 3-in-1 flow meters, or you can use pressure sensors to track those things. But it's important to measure both flow and pressure in this case, because pressure loss is always related to flow. If there's no flow, there will be no pressure loss. You need flow to generate pressure loss. And well, how does it look in practice? Well, this is an example where you see the red line is from the red flow meter, in this case of flow, pressure, and temperature, 3-in-1, and then the blue line is from the other one. And then you can see if you subtract those two, and the difference is on the right axis, you can see the pressure loss. And you see that there are peaks up to 1 bar, and on average there might be like a half a bar of pressure loss in this system. And this is quite a huge saving potential. It's about 7% of the energy bill if you're able to save 1 bar in your overall pressure. Another example, if you look at dryers, and especially heat regenerated desiccant dryers, they use heat to regenerate the internal desiccant. And if you put a temperature sensor downstream of the dryer, you might see some peaks. And it's normal that there will be some peaks because there's always some hot air coming out after the column changes. But if it's too high, that might indicate an issue with the dryer. And you see here a real graph with flow, with pressure, and then with temperature. And you see those big peaks. Every time that the column is switching, there is a peak. And here's one more example of another factory where you see there's the day-night change. You see that in the bottom you see already that the green line is not completely steady. It's a little bit wiggling up and down, but then you see those huge peaks on top of that. So in this case, the dryer was not working properly, and it had to fix an internal component. What you also can do with, if you have a fridge dryer, you can also look at temperature difference over the dryer as a function of flow. And in that case, you can also see when the dryer is undersized, because then the temperature difference, you will see that the outlet temperature will start to rise, and the desiccant and the fridge dryer is not able to cool down the air anymore. Another way to use flow, pressure, temperature sensors is to look at downstream production equipment, very specific, zoom into one machine. In this case, there was a client that had a robot which was used to clean off the flakes of metal parts from automobile wheel rims. And they used this nice homemade nozzles here, you see at the right corner, right top. And they thought they were doing a pretty good job. And then a sales guy came and he said, well, maybe you need an engineered nozzle that might save you some money. And then sometimes customers are a little skeptical about that. But well, they gave it a try and they used a flow meter to check actually how much they could save. And in this case, the savings were quite interesting. With the do-it-yourself nozzle, they consumed about twice as much air as with an engineered nozzle. So the total savings at a couple of these machines were around $9K a year. And the return on investment was a couple of months. I think they invested around $1,500 or $2,000 for the engineered nozzles. So it's a good way to make decisions based on this kind of data before you invest any money. Bidirectional flow measurement, Tim already talked about that. Bidirectional flow can be very important, not only in looped networks, but also it might reveal issues with a non-return valve or with a leaking blow-off valve of a compressor. If you have the flow meter downstream of that, the compressor is off, you might see flow coming back into the compressor, which is not good, obviously. It could be a leaking gasket, something simple like that, or it could be something else. You can also reveal sometimes oscillations in the system with a bidirectional flow meter. So it's sometimes very useful. You see in these graphs, if you it's the same signal, but then unidirectional, you see you can make wrong conclusion also if you're not measuring bidirectionally. Receivers are you can compare them to filters, and not filters for air, but like signal filters, like electrical filters. If you're measuring up or downstream of a receiver, you will get a different signal, depending, of course, on the size of the receiver. The input flow is most of the time equal to the output, unless there is a drain in the receiver which is leaking, which can also be revealed by this. But suppose the receiver is closed, then and it's not leaking, then you can see that at the input there will be still a very irregular pattern showing all kind of peaks, and downstream of the receiver you might see a smooth line filtered out, and also sometimes vice versa. It depends a little bit on the equipment, of course, up and downstream of the receiver, but it works as a filter, so you should be aware of that to draw the right conclusions. So coming to the end of the presentation, some tips and conclusions. One thing, it's important to be alert on the measurement uncertainties and be reasonable when discussing, for example, compressor capacity or compressor efficiency. You're not a test lab. You're not in a test lab. You're in the field, so there's a lot of things that might influence the measurement. If you combine signals, you can reveal more savings potential, and you can reveal more issues. And in many cases, it's important to know the process and instrumentation diagram before you can do a good analysis of the system. And when it's time to really optimize, you should hire an expert and or auditor to help you. Or if you need any help with resolving or with analyzing the results, hire an expert, maybe also on a particular part of the equipment to come to the right conclusions. Okay, thank you very much for your time and your attention.